Foams are very much like emulsions, but are different because instead of having drops of a fluid inside a second fluid, they have bubbles of air inside of a fluid. Nevertheless, you can have exactly the same effect. You can have a foam that is solid, you can have a foam that's liquid-like, and it's a way of putting air bubbles inside of a fluid. Of course, one of my favorite foams is the foam that you see on the top of a beer. The beer foam will last for different amounts of time. Guinness would last for a long time, Budweiser for a much shorter time, but still the head on the top of a beer is just a foam. They're bubbles of air inside of the continuous phase, which is the liquid from the beer. Nando also made foam. He made sea foam and carrot foam. In both cases, he essentially mixed in or whisked in air to make bubbles of air inside of the fluid. Another very good example that maybe you're familiar with, I like very much, is the foam on the top of a cappuccino, the milk foam. Milk is something that just as it makes a wonderful emulsion, it can also make an excellent foam. And in order to stabilize the bubbles, to keep the bubbles from coalescing, from joining together, to make them stable, just as you had to have in the case of an emulsion, so too in a foam you need a surfactant. In this case, the surfactant goes to the interface between the continuous phase, which is a liquid, and the air. Another very, very good example is whipped cream, which can become a very thick solid, an elastic solid. So the amazing thing about a foam is that you're mixing a fluid and a gas. A fluid wants to fill a bowl, sit at the bottom of a bowl. A gas wants to expand everywhere. You mix them together and you make bubbles of the gas inside the fluid, and you can end up with something that is a solid. It's just like an emulsion. You get exactly the same effect, and we can understand it in exactly the same way. So foams, you need to put many drops, many bubbles of a gas inside a fluid. You need to have them stabilized by a surfactant, and the result is that you can avoid the drops from destabilizing in exactly the same way that you have with an emulsion. So the drops in a foam can destabilize either by coalescence or by Oswald ripening. Both of them lead to coalescence just as they do with an emulsion. Here, in the case of a foam, the drainage, the fact that you get the creaming of the bubbles going to the top of the foam, is much more severe than in the case of an emulsion, because the density difference between air and any liquid is always much greater than the density difference between two liquids. So the bubbles tend to cream, go to the top, and therefore destabilize in a foam much more easily. In order to stabilize the foam, again, you must use a surfactant. In the case, if you think to what Nando did when he made the sea foam, he added a surfactant. In that case, the surfactant was lecithin. In the case of the carrot foam, he didn't add a surfactant. He used the carrot itself, the surfactants in the carrot itself, as the surfactant. But in both cases, you absolutely must have a surfactant to keep the drops, to keep the bubbles stable, to keep them from coalescing. And that's the key to having a foam. What Nando did was he mixed the foam. He whisked in air to make the foam. But there's a second way, a completely different way that you can make a foam. And you know that if you go to a coffee shop and they put foam on the top of your coffee or whipped cream on the top of your coffee, they use one of these whipped cream makers. In that case, you make a foam in a completely different manner. What you do is you take a compressed gas. Typically you use nitrous oxide because nitrous oxide is very soluble in things like milk. You mix the compressed gas with the milk under high pressure. The gas at that point is at a sufficiently large pressure that it's a liquid, and the two liquids mix and essentially make an emulsion of the compressed gas, which acts like a fluid, in the continuous phase, which say is the milk. Then when you spray it out on the top of your coffee or on the top of your drink, the pressure decreases because you spray it out of the can, it goes to the low pressure of atmosphere, and the gas, which is emulsified and formed and is high pressure, so as a liquid, expands and forms small pockets of air or bubbles of air. There are other ways of stabilizing a foam in addition to just having surfactant and keeping the volume fractions high. You can also force the continuous phase to become, rather than a fluid, to become elastic. The way you can do something like that is to gel the continuous phase. That's a very common way that chefs use to create, for example, desserts. A mousse is a foam where the continuous phase has been gelled. You can add some gelling agent to form it into a gel, or you can freeze it, or you can solidify it, like having something that's a fat and having airdrops in a fat to solidify it just by lowering the temperature. But if you solidify the continuous phase, you can prevent the airdrops from creaming and the foam from breaking. Here are some microscope images where we look at the foam. You can see that there are bubbles of air inside the fluid. Here's some pictures of a whipped cream. You can see the bubbles of air inside the fluid very nicely in these microscope images. Now, a foam can become elastic, and it has an elasticity that is exactly the same as an emulsion. It's the formula, the description of the elasticity of the foam is exactly the same as an emulsion. It cannot be solid until the bubbles pack at such a high density that they must deform. The equation for the foam becoming elastic is exactly the same as that for the emulsion. It depends on the volume fraction, the difference of the volume fraction from the critical volume fraction, and it depends on the surface tension of the bubbles that are pulling them together and the inverse of the radius. And again, the bubble inside a foam has to have a Laplace pressure. Its pressure must be larger than what you would see if it weren't confined to a bubble. The larger the pressure, the smaller the drop. As you make the bubbles smaller, the Laplace pressure goes up. As you make the bubbles smaller, the elasticity of a foam goes up.